Yeah, so let's proceed with the first one by Cristian Reyes of his bachelor thesis called Untitled Chapter, Image Retrieval for Finding Objects in Live Logs. So Cristian, whenever you're ready, you have 20 minutes to begin your work.
Okay, good morning. I'm Cristian Reyes, and I'm going to present my bachelor's thesis called Time-Sensitive Egocentric Image Retrieval for Finding Objects in Live Logs. I was doing this thesis at the Dublin City University, and I was advised by Eva Moedano and Kevin McGuinness there, together with Xavi Giró from UPC through video calls. So this is the outline of the presentation, and I'll start with the motivation. So live logging is the action of recording and tracking data related to our daily lives. We have several devices to do that, like smartwatches, wearable cameras, or even our mobile phones. But the challenge for research is how to extract value from this new data. Nowadays, people are used to wear smartwatches, and they can track how many steps do they do during the day, or how many hours do they do, based on the information captured by motion sensors. With wearable cameras, there are some advances in the medical field, such as helping people with mental disease, like Alzheimer's. In this work, we tried to build an application focused on general population. So I'm sure most of you have lost your phone sometime, and then you get in panic and try to find it somewhere. So we think that egocentric cameras may help. Egocentric cameras are devices that are worn on the chest or the glasses, and they take pictures every certain periods of time, such as 30 seconds. So we can use them in order to find out where was the last location that the camera saw the object, so it may help to find the object. But the problem here is that these cameras can generate up to 2,000 images daily. So if we have to review them manually, this is a huge task. But then when we find the image that we need, we can determine that maybe I forgot my phone at the cafe. So in this work, we aim to make this process automatically. So let's define the task. The task is to retrieve a useful image for the user in that problem. And how are we going to do that? We are going to explode both visual and temporal information. So the system we have designed has two inputs and one output. The first input is the query. So what's the object I'm going to look for? And the second input are the daily images, which I will also refer as target images. That are the images that are captured by the wearable camera. And then the output is a ranking of the daily images based on their likelihood to help the user. Internally, the system has several stages, and we also can approach each one of the stages by different techniques. We included 4 different flags in order to choose what configuration do we want to use at each stage. So in the methodology section, I'm going to explain deeper all these stages. So the first stage consists on doing a visual ranking based only on the visual information rather than the temporal. This ranking calculates scores related to each target image based on their likelihood to contain the query object. Then it must be said that this visual ranking doesn't need to be helpful for the user because we don't have here the temporal information. So we want to enhance this by applying 2 more stages. The first one is a selection of candidates that basically splits the visual ranking into 2 subsets. The first one contains images that are candidates to contain the object, and the second ones are discarded images. So we assume here that the object is not contained in them. And finally, we apply a temporal reordering to both subsets to get the final ranking that will be given to the user. I'm going to explain deeper how the visual ranking works. We used a visual search engine which is based on convolutional neural networks. And what it does is it extracts local features from the images, and then we will use them to compare. Okay, I'll start again this part. So to build the visual ranking, we used a visual search engine that aims to compare images. In order to compare them, we need to build descriptors of the images. These descriptors are numerical vectors that allow to make this comparison. To get these descriptors, this engine uses convolutional neural networks to extract features of the images. Then these features are gathered using the back-of-words model. This model has a code book of code words which are trained with these features. So then we have visual code words, and what we do is we build. Okay, I'm not training this. Okay, so when we extract the features, we build a code book of visual code words, and then we assign each feature to a code word. Finally, the image is described as the histogram of its code words. This is a very useful approach because we can keep the information of the location of the patches of the image. So then it will allow to enhance some parts of the image among others. To make that comparison, we built a descriptor of the queries, and then we built a descriptor of each target image. In order to build the query descriptor, we use 5 visual examples that depict the object from these different points of view. Then we average their histograms by using 3 masking strategies. The first one is just averaging the histogram of the 5 whole images. Then we use only the visual words that fall inside the bounding box. And finally, we use a soft bounding box in order to enhance the center, the bounding box, but also take into account the background. Regarding the target, what we do is 3 masking strategies also, but they are slightly different. The first one is also using the full image. Then we have another strategy that consists on applying a center bias. That means that we are focusing the attention in the visual words of the center of the picture, and we are downweighting the surroundings. And finally, we have studied the usage of a silency mask. The silency masks uses a silency map. Silency maps are maps that predict where people would look at the image. So by using this information, we try to focus on the most relevant points. After the visual ranking is done, so we have the query images and the target, we apply some pre-processing, and then we compare them. And we get a score for each image, and we get this visual ranking. So now let's see how do we split into the candidates and discarded subsets. Okay, we studied 2 different strategies to do that. Forget about this. And the first one is using an absolute threshold. So that means that using the scores of the visual ranking, we want to set a threshold, and the images that have a higher threshold, a higher score than the threshold, are considered as candidate. And the other approach is using an adaptive threshold that's called nearest neighbor distance ratio, which takes care of the 2 first values, the 2 first scores of the visual ranking. But the problem here, although they are really simple approaches, is that we have to decide what thresholds do we want to use, what values. I will explain later how do we do that. And finally, to build the final ranking, we studied also two different strategies. The first one is applying just a simple timestamp sorting in both subsets, but then we realized that because of the redundancy of the egocentric images, the top of the ranking seemed like this. So we got several similar images, but the problem is that if an image is not relevant to the user, the following ones will not be relevant to the user. So to solve that, we decided to apply a temporal diversity technique that we called interleaving, because it's quite similar to the interleaving used in digital communications. And what we do is we order the images. So here is the end of the day, and then we are going backwards. And we assume that each block of green images are representing the same scene. So we want to pick a candidate, a representative of each of these blocks. So we pick the first one of each block, then the second one, then the third, and so on. So finally, we reorder the images of both subsets with this technique, and we get the final ranking. Here we can see how this diversity helps, because we have introduced here two new locations at the top of the ranking. Okay, so this is the methodology, but now we aim to determine what's the best configuration for the system. To do that, we need to be able to compare different configurations. So we need somehow to evaluate them quantitatively, to be able to compare numbers. And to do that, we need four things: a data set of images that would simulate the images captured by the user with a wearable camera, a set of queries that would be the collection of objects that I will be able to find. The ground truth is a set of judgments saying whether an image is relevant or not to the user. And finally, a proper metric that describes the user experience with the system. The data sets we were studying are these two ones here. Finally, we decided to use the one in the right, because it has several images that allow to understand a general behavior of the system, but also images were taken using the autographer wearable camera that has a wide-angle lens. So this made the images more likely to contain personal belongings. Regarding the queries, after analyzing the dataset, we decided to work with these four categories that are phone, laptop, watch, and headphones, and we used these images to build the query to bring it to the system. As you can see, those images contained most part of the object in them. In order to annotate the data set, because it wasn't annotated for this task, we decided the first approach we did is to annotate the three last occurrences of each object in different scenes. But then we realized that the system was expected to find the three occurrences, so it wasn't really what the user needs here. So then we decided to move to the second strategy, that was annotating the last occurrence. But what happened here is that maybe when we saw the ranking qualitatively, we saw that it was performing better than what metric was saying. And the cause here is that neighbor images can be helpful also to the user, but they don't have to be the last one image that contains the object. So in order to solve that, we decided to finally annotate all the images that were composing the last occurrence of the object, but in the same scene. And this was very related to the metric also. The first two approaches that we did here, we were using the mean average precision. And this metric takes care of all the relevant images of the ground truth. But then we decided to move to the mean reciprocal rank. This metric takes care of the first relevant result of the ranking for the user, and that's what we wanted. Finally, we defined this AMRR to refer to the average of the mean reciprocal rank across all days. Okay, so if you remember, I wanted to remind you that we had to decide two threshold values, and how did we do that? We divided our annotated data set into two subsets, 9 days for training and 15 days for test. The idea here is to use the training set to find the better values for these thresholds, but then use them for the test set. We have also to train this codebook of visual words. In order to do that, we used these 9 days that had around 30,000 images, and we extracted around 80 million feature vectors. And then we applied a clustering algorithm in order to build the codebook that was created by 25,000 visual words. Then, in order to pick the threshold values, what we did is we performed a sweep from 0 to 1 of the threshold, and we computed the AMRR over the trained set. So then this metric can be understood as a function of the threshold. And we picked the threshold with the highest performance. It must be noticed that the threshold, the training has to be done in the same conditions that we are going to perform the test. So we had to make a training for every one of the configurations that we have. But the good news here is that the optimal threshold remained to be the same if we moved from the no diversity to diversity, or changing the pre-processing applied to the target images. So before showing you the results, I would like to summarize all the parameters that we have in the system. We have to decide how to make a pre-processing for the queries that can be full image, hard bounding box, or soft bounding box. Then we have to decide what to do to the target images, can be full image, center bias, or saliency maps. We have to decide whether the threshold is adaptive or absolute. And finally, if we use temporal diversity or not. Okay, so in this table, we show all the results for all the possible configurations. The first, the rows are the possible approaches for the query pre-processing. Then each of the tables show the results for a specific approach for the target images. Then we have in these rows, in these columns, the possible thresholdings, applying a simple temporal reordering, and then with the interleaving approach. And finally, in the first column, we have our baseline. That would be the most simple approach, that would be ordering the images by their timestamp. And we also added an intermediate stage to be able to understand what is the visual ranking doing and what's the temporal part improving. So regarding these tables, we can see that the first of all and most important thing is that the system is helpful because it improves the results versus the baseline. Then we can see in several cases that temporal diversity improves the results. We can also see that objects are not always in the center, because comparing when we use full image for the target images or we use the center bias, the performance gets worse, and that's probably because the objects are in the surrounding parts of the image. Another conclusion that we can take is that saliency maps, there are some configurations that are not helpful. There are others that do not seem to improve the results, but when using full image in the query, it outperforms any other approaches. And finally, there's another important thing that we can see in these tables, that the parameters do not seem to be independent, because if at the very beginning of the project we had decided to choose the soft bounding box for following the experiments, then when applying the saliency maps, we would have reached this value that is lower than the first one. So we had thought that saliency maps do not help. But then we realized that the best result is when combining with full image, that we hadn't seen this at the very beginning. So parameters are not independent, and this makes us and this says that what we have to do is to optimize, first of all, the visual part of the system using an appropriate data set and ground truth for this, and then we can evaluate the performance at the ending using also the temporal information. Okay, and here I didn't want to add these conclusions because it's almost what I have been discussing here, so it's almost the same. I wanted to ask you if you wanted to keep this or not, and I would like also to say that this work was presented at the middle stage on this workshop on egocentric vision at the CVPR, and I would like to acknowledge Noel, Cathal, and Albert for their technical support. And that's it. Thank you.
Okay. Exactly 20 minutes. So that's pretty timing.
No sé, això el Xavi. Jo he posat el ministeri.
In this case, he had a chapter, I think I put it there.
Yeah, we put it in the CVPR.
So he's paying me. He's paying part of and he pays for the trip to CVPR program.
What?
You haven't gone to the street.
No, I
No.
You will.
So I don't know if he should be thanking.
Ah,
Yeah, I mean, if you would be presenting, I guess so. But,
Ah.
it's, I don't know. It
Well,
doesn't-
these acknowledges are from the poster at CVPR, so I can remove whatever.
just give the Erasmus an idea. This thing, if you want.
Okay.
Yeah, and I don't think that quite technical support, right?
Yeah, but I didn't know what to put here.
Just remove the technical support and
Okay.
I'll leave the pictures.
About the photos.
yes.
And the photos of both Albert and
Do they have better photos?
yeah, do they have little
They,
photos?
they always say that
Because
they will give better ones.
Because
They never.
they are not very serious at this photos.
It's okay.
So, no, if you see the one on the
No,
top,
Joseph one is really bad.
Yeah.
and Albert, well, it's not as serious as
Just
the
ask
other two.
ask them. I mean, tell them like, we're using your photos. And you need to have better
I
ones.
don't know, for the repo I have to put
But that's what they have on the website.
Yeah.
It's a nice photo, why not? Yeah, but you haven't seen one
He gives
from
that
Jose.
photo.
I've not seen the other one.
in a forest study.
Yeah.
You just remove technical support again. Just take the Erasmus and video.
Okay.
So they are not serious.
But they have put the
expected,
photo.
so
Yeah, they like it.
these ones are more serious than this
They
one.
don't care.
Yeah.
This image is the image of the
Ah, okay.
They don't care.
Do I stop this, Xavi?
should continue.
It's just being recorded by. And they're the ones who are in charge.